On March 19, 1940, 50 Royal Air Force Whitleys and Hamptons took off from English air bases to bomb a German seaplane base on the island of Zilt off the Dutch coast. In spite of pilot reports of direct hits on facilities, post-strike photography revealed no evidence of RAF action, suggesting that the aircraft, which had been dispersed by weather, had bombed a number of other locales on the Dutch coast. This dubious feat was followed up by a May 27th Whitley sortie, where the crew rejoiced in their success in bombing a German airfield in Holland until, when upon breaking out of the clouds over what they thought was their home airfield in Yorkshire, they realized they were over Liverpool. Fortunately, the actual and fortunately bloodless recipient of their bombs was the RAF Fighter Command Field of Basingbourn in Cambridgeshire. The resulting panic over navigational shortcomings may be seen in a June 1940 program to develop a navigation system that was to detect magnetic fields of electrical transmission lines so they could be followed to target installations or cities. The Battle of France further highlighted the problem, as the inventor of the G hyperbolic system, Dr. Robert Dippy, noted, quote, less than 10% of bombs dropped were falling on worthwhile targets, end quote. We should therefore not be surprised that navigation was a primary point of consideration during the Tizard mission, and that when Alfred Loomis founded the radiation laboratory at MIT, he put long-range navigation at the same top priority as airborne intercept and gun-laying radars. This investment, as America entered the war, was borne out by operational experience over the next 3.5 years. An 8th Air Force assessment of wartime operations determined that on only 73 days per year did the weather permit both airfield operations in England and visual strikes on targets in Germany. Thus, not only were electronic navigation systems essential to wayfinding for aircraft and vessels, but also for targeting. Victory in the Second World War was a victory of cooperation. Often this cooperation was as much intellectual exchange as it was brute force. Nowhere in the web of Allied or Axis alliances was this partnership more effective than between the United States, Britain, and her Commonwealth. The 1940 communication known as the Tizard Mission was merely the beginning to a more complex technical discourse that played out in a myriad of operational experiences. Some of these dialogues would resonate well beyond the war. Today, much of daily life is touched by the precise timing and navigation signals of GPS. Systems like GPS did not originate in isolation. Instead, they emerged from a continuum of navigational systems that had their roots in the Tizard Mission. Hyperbolic systems worked by precisely measuring the time delay between reception of signals broadcast from a pair of stations at significant distance and geometric variation from the user. In broad terms, the wartime advent of hyperbolic navigation marked an important advance in the navigational arts. It was the first form of electronic area navigation that was both reliable and accurate. Oops, sorry. The navigational disasters that I alluded to in the introduction led to the rapid development of a system which would be critical to the European theater in the last 3 years of the war. This was G, as in grid, for the hyperbolic lattice of the charts required to use the system. It was the brainchild of one of Watson Watt's engineers at the British Telecommunications Research Establishment, Robert J. Dippy, who was looking to address the challenges of blind landing for airplanes in 1937. As in radar, the combination of the cathode ray tube and the crystal oscillator allowed measurements in the microsecond range. In peacetime and during the phony war, Dippy's concept had been shelved because of the resources required. But the disasters of mid-1940 resulted in a crash program to bring it to fruition. Dippy began testing G in late 1940 with results that exceeded expectations. Wellington's of 115 Squadron undertook the first operational use on the evening of August 11, 1941. But another year passed before Americans would become involved with G. By December 8, 1942, 10 American G navigators had logged 500 hours with the equipment, finding it easy to operate, and several considered it to be the best navigational aid at their disposal. In February 1943, 3 raids occurred with G-equipped B-24s in the lead. However, General Ira Aker was not overly impressed, stating to General Hap Arnold, commander of the U.S. Army Air Forces, quote, "We have run across 2 very disappointing factors. One is that this gadget has not nearly the range in daytime that it has at night. The other is that the Germans have discovered a method for jamming it," end quote. This rejection lasted for less than 6 months. and by midsummer 1943, General Acre enthusiastically gushed to Air Chief Marshal Sir Charles Porter that, quote, "The crews in our 8th Bomber Command who have used G are most enthusiastic about this equipment. There is a probability that during the coming months, our crews may be going out or coming back in darkness. As a navigational aid, it would be desirable to have all of our aircraft equipped with G," end quote. In conjunction with this ringing endorsement, on August 5, 1943, Acre requested 2,000 G units from Porter to be delivered at a rate of 300 per month. At the end of August 1943, the 8th Air Force had 251 mission-ready G-equipped aircraft and another 40 outfitted for training, with a total of 133 G-certified navigators. 8 months later, there were more bombers with G than without, and by the end of the war, every American heavy bomber in Europe had a G set, totaling more than 2,500 aircraft. American reliance on British electronic navigation is an often overlooked part of the Allied victory, but it is one that should be remembered. That is not to say that G was a panacea for the Allies. German countermeasures grew increasingly effective. However, a separate, unused frequency had been set aside for D-Day to ensure a brief window for the airborne drops to proceed without interference. The German recognition of the new frequency and the calibration of the jamming transmitters typically only took about 90 minutes, but in the chaos of the day, the Germans were unable to jam at all. The 9th Troop Carrier Command's 844 C-47s and 150 gliders carrying 15,000 airborne infantry were led by 20 C-47 Pathfinders equipped with SCR-717C radar, AN/APN-2 Rebecca receivers, which you can see out in the lobby, and G. Here we can see a section of a remarkable Supreme Headquarters Allied Expeditionary Forces document from the National Archives here in College Park, dated June 29, 1944. And it's depicting the attempt to coordinate the positioning of G transmitters on the continent with the likely advance of the front lines and areas of operation of the French resistance, which you see in the cross-hatched areas here in red on the chart. So kind of an extraordinary piece of history. G had an important secondary legacy for the Allied war effort. Its receivers could be used to pick up radar ranging beacons as part of the blind bombing system known as GH. Given the difficulty of equipping large numbers of aircraft with the expensive and bulky H-2X radar, not to mention its trained operators, GH, its range limitations aside, offered a more versatile blind bombing capability for more aircraft and at far less effort. This 8th Air Force chart only hints at the growing significance of GH in blind bombing, as it does not include RAF usage or that of the 9th Air Force, where it was far more important since its medium bombers were too small to carry H-2X radar. The United States had become aware of G during the Tizard Mission when Dr. Taffy Bowen described the principles of Dippy's hyperbolic lattice system, which had yet to be put to a real-world test. This moment was a particularly important critical historical contingency as it began to focus Alfred Loomis's personal interest in precise timing on the problem of expanding the range of a G-type system, which, without an infrastructure in Nazi-held territory, could only reach to the Ruhr, much less cover the North Atlantic. A day after Bowen revealed G to Loomis on October 12, 1940, Loomis sketched out a network that did not rely on line-of-sight synchronization. This would become Loran. Britain continued to play an important role in the development of Loran, with Bowen attending the project kickoff meeting in December 1940. A British embassy liaison officer, squadron leader Hignett, also participated in later meetings. Unfortunately, neither was versed enough in G to allow true coordination or cross-pollination as Loran began development. Dr. Touch of the British Air Commission was finally able 9 months later to provide critical information on the practicality of creating a multiple trace indicator, something already demonstrated on G. In January 1942, Britain supported Loran development by hosting a team of observers at Bermuda to isolate the system's skywave performance with the first 2 experimental Loran transmitters at Montauk Point, New York, and Fenwick Island, Delaware. 6 months later, Dippy, fresh from his successful implementation of G with the TRE in Britain, arrived at the Rad Lab to help finalize design of Loran airborne receivers that were interchangeable with G receivers, both in size and power supply. He also played a critical role in the early design of ground station timers. Loran collaboration began in earnest with the Canadian government in May 1942. This cooperation was essential as North Atlantic coverage would require stations based in the maritime provinces. From that point on, the Royal Canadian Navy played a prominent role in Lorraine development. The first test chain of 4 stations had its northernmost sites located in Baccaro, I hope I pronounced that right, and Deming, Nova Scotia, which were up and running by October 1st. In July 1942, a joint Canadian and American team set out for Newfoundland and Greenland to locate the 5th and 6th stations. Construction for these northern stations was run out of Goose Bay, thus beginning the close American and Canadian partnership on nav aids and radar in the far north that has persisted to the present day. Synchronization of this first chain occurred on May 30th, 1943. However, even before then, the British Admiralty had begun to take interest as the U-boat wolf packs had begun their second happy time, as they called it, and as the Murmansk convoys were taking significant losses. In exchange for the Lorraine hardware, the Royal Navy agreed to establish and operate 3 Lorraine stations under the guidance of U.S. personnel, the first of which was in Vik, Iceland. The second station was at Scuvane in the Faroe Islands, and the third at Mingersta in the Hebrides. Eventually, the RAF added a station in the Shetlands, so coverage could be extended to the Norwegian coast for Coastal Command aircraft patrols to protect the Murmansk convoys, including the campaign to sink the Tirpitz. The Royal Canadian Navy began Lorraine operations for convoy escorts before the end of 1942, and by the end of the war it had equipped 120 corvettes, 40 frigates, and 2 cruisers with receivers. Royal Canadian Liberators, based at Gander, made great use of Lorraine starting in 1944. RAF Coastal Command trained its navigators in Lorraine at Mulligamore in Ireland. All RAF and U.S. Navy aircraft operating under Coastal Command, about 500 in total, were carrying either a G or Lorraine set by the last year of the war, depending upon their patrol area. On VJ Day, 20 Lorraine stations on 4 continents, constituting 72 Lorraine stations, were in use. The American Army and Coast Guard operated 59 of these, but the remainder were operated by British and Commonwealth military personnel. Europe and the North Atlantic were not the only areas of active British participation in the Lorraine network. The RAF requested and received permission from the U.S. Joint Chiefs to reallocate U.S. Navy station equipment for a new East India coast chain that would give coverage over the Bay of Bengal, which went online April 15, 1945. The RAF Bengali station of this chain was also an anchor of an SS Lorraine chain that covered the Himalayas to aid transport pilots flying the hump. That chain went online March 15, 1945. If the close partnership of Americans, Britons, and Canadians made Lorraine a great success, the RAF played a particularly significant role in Lorraine's ultimate wartime development, Skywave synchronized Lorraine, known as SS Lorraine. A major coverage limitation of Lorraine was that signal propagation required that the slave stations be within ground wave reception distance, up to 450 miles, of the master station for the effective geometry of the system. Given the distances involved, hardwiring the stations together was not a practical option. However, beginning on November 5, 1942, the Rad Lab's J.A. Pierce began development of a system where slave stations could be synchronized by skywaves, giving an overland distance between stations of nearly 1,400 miles. Unfortunately, because reliable E-layer reflections were only available at night, the system would not be functional during the day. The RAF actively participated in joint meetings with the U.S. Army, Navy, National Defense Research Committee, and the Rad Lab's Division 11 on development of the system, which clearly had significant potential for operations over the continent. A breakthrough on SS Lorraine occurred on September 20, 1943, when the first pair of test stations began operating and maintained synchronization for several hours. The test program featured 4 aircraft, 3 of which were operated by U.S. crews and 1 by the RAF. In October 1943, the RAF took responsibility for the final assessment, which determined that accuracies were in the 1 to 2 mile range, which was as good or better than conventional Lorraine. The Joint Committee then decided that RAF night long-range pathfinding took precedence and began work on a European SS Lorraine chain that would guarantee accurate nighttime navigation into Poland and eastern Germany. Beyond requiring close Anglo-American cooperation, the desired coverage area had significant geopolitical implications. The initial proposal featured stations in Scotland, North Africa, and the Soviet Union. The sensitivity of an established Lorraine station on Soviet soil proved insurmountable, and the geometry had to be reconfigured for a station pair of Port Erroll, Scotland, synchronized with Bizerte, Tunisia, and Oran, Algeria, synchronized with Apollonia, Libya. At 20,000 feet, this architecture gave coverage for 2/3 of Poland. SS Lorraine equipment equipped the tip of the RAF Spear in its nighttime deep penetrations of German airspace, consisting of 5 groups, 350 Lancasters and 20 Mosquitoes, and the 8-group Pathfinder force of 170 Lancasters and 200 Mosquitoes. The heavy aircraft of the Ferrets, used by 100 Group, also carried SS Lorraine. The first operations occurred in October 1944. Sustained SS Lorraine strikes on Berlin began in February 1945 and continued through the end of the war, with the Lorraine-assisted sortie total reaching 22,000 in RAF Bomber Command. Perhaps the best sense of the joint implications of Lorraine development may be seen in a September 19, 1944 flight of a RAF Transport Command Dakota, which we can see depicted on the chart here. And it made a circumnavigation of the North Atlantic to determine the comparative coverage and performance of transoceanic navigation aids and methods. Lorraine provided the best coverage of any of the systems tested. The report's final assessment stated, quote, "It is considered that Lorraine requires more experience in use than G, but when this experience has been gained, accuracy of a higher order can be expected. The mean of 3 readings can be taken and plotted on the Lorraine chart and transferred to the navigator's chart in 10 minutes, end quote. The American abandonment of Lorraine C in 2010 and the UK's recent embrace of E-Lorraine as a hedge to the vulnerabilities of GPS is a somewhat ironic twist to the relationship that began 75 years ago. While G did not last much beyond World War II, other wartime navigation targeting systems have had similar narratives of enduring Anglo-American cooperation. I could have told much the same story with Decca or Choran, for instance. The technical wonders of the 20th century all have an international character shaped by cooperation, competition, and confrontation. The wartime hyperbolic navigation systems that grew from the two-way interchange realized in the Tizard Mission represents technical cooperation at its most effective. The swords into plowshares aspect of Lorraine, which had significant post-war civilian utility, makes it an effective case study in how cooperation created systems of far greater effectiveness than if they had been developed in nationalized isolation. The geographic distribution of transmitters, particularly for Lorraine, required a degree of international cooperation that is still absolutely essential for present-day systems like GPS, which would be inoperable without access to sites like Diego Garcia. If the history of Anglo-American cooperation in wartime electronic navigation has long been neglected, its legacy can still be felt in daily life through the largely invisible world of today's electronic infrastructure. Thank you.